Hi everyone, my name is Makumba Gerard of EduMath. In this video, we are going to look at how to find the errors within a differentiable function. But hey, before we continue, if you are new here at EduMath, consider subscribing and hitting the notification bell such that you can be notified of our new videos that we make every day. So let us get started and see you there. Errors in differentiable functions. So let y to be equal to fx, where smaller y and x are approximations of capital Y and capital X respectively. So if we can recall from our first video about errors and approximations, we defined an error mathematically as being equal to exact value minus the approximate value. So if delta x and delta y are errors in capital X and capital Y respectively, then we shall have delta x being equal to capital X, which is our exact value, minus the approximate value, which is smaller x, and this means that capital X is equal to smaller x plus the error in x, this crossing, and we have the error in y is equal to the exact value minus the approximate value, and this also gives us that capital Y is equal to smaller y plus the error in y. Right? So when we treat this function y with its errors, we shall have smaller y, right, plus its error y, giving us f into bracket. Let's treat x with its errors, so we shall have x plus delta x. Right? Next, we are going to get it from Taylor's series. We have that fx plus delta x, this is expanded as fx plus delta x, f the first derivative of x plus delta x squared times the second derivative of x divided by 2 factorial plus delta x power 3 times the third derivative of fx divided by 3 factorial plus this continue. So the terms of the Taylor series continue like that. So since fx plus, since fx plus delta x is equal to this, okay, so this implies that y plus delta y is equal to fx plus delta x, f derivative x plus delta x power 2 double derivative or second derivative of x divided by 2 factorial plus delta x power 3 third derivative of x divided by 3 factorial plus they continue. Okay, now from here, since we have delta x being small, that means delta x squared and other higher powers of delta x approximate to 0. So a very small value, when you give it higher powers, it will always tend to 0. So that means this part here going this side are going to be 0 terms. So they will not be significant. So we shall remain with y plus delta y, giving us fx plus delta x, f derivative of x. The terms which follow here are now zeros because of this reason here. Now we are interested in the errors in this differentiable function. That means this y will have to cross to this side. So we shall remain with delta y being equal to fx plus delta x, f derivative of x minus y. But we said that y is equal to fx. So where there is y in this equation, I'm going to put there fx. So we shall have delta y being equal to fx plus delta x x f derivative of x minus, now this is fx. So fx and fx will vanish and we have delta y being equal to, we have remained with delta x f derivative of x. So from here, this here is the error in y, in a differentiable function y. So from here, we go ahead and get the absolute error, which have magnitude y being equal to the magnitude of this whole term, delta x f derivative x. But because f derivative x is a function, so we cannot bound any function, meaning that the bound or the magnitude signs will only apply on the error. So we shall have delta y and a magnitude being equal to delta x and a magnitude f derivative x. And from here we can go ahead and get the relative error, which is equal to the absolute error divided by the exact value. So relative error is equal to this here, magnitude delta x f derivative of x divided by fx. Fx is our exact value. So this is what gives us the error in any differentiable function. Let's have an example. Given that the error in measuring an angle is 0.5, find the maximum possible error in sin x divided by cos x for x equal to 30 degrees. First of all, you realize that this here, what is given to us here, this function is a fraction. So that means we have to think of how to handle errors in division. So I will start by saying let smaller a to be equal to a function sin x and smaller b to be equal to a function cos x, such that if we say let z to be equal to a all over b, we shall be referring to this. So from maximum possible error in z is now going to be equal to the error in a, because this here is a differentiable function, a is a differentiable function as well, and b as well. Error in a all over a plus the magnitude of the error in b divided by b itself. Why am I using deltas here is that these are both differentiable functions. So we have to go ahead and differentiate a, which is here, differentiate b, which is here, with respect to the angle x to get delta a. So therefore, differentiating a with respect to x, this here is going to give us, when we differentiate this with respect to x, we shall get cos of x. And from here, when we make delta a the subject, this is going to be delta x cos x. Taking the magnitude for this, we shall have magnitude delta a is equal to the magnitude of delta x cos x. So we shall have magnitude delta a being equal to delta x cos x. We go ahead and we also get delta b. So from here we are going to differentiate with respect to x. So we shall have delta b with respect to x. This here is going to be negative sin x, right? And this means delta b is equal to negative delta x sin x when you multiply. And bounding this, we shall have delta b and the magnitude to get the absolute error being equal to the magnitude of negative delta x sin x. Delta b being equal to, we bound on the error, negative delta x sin. The magnitude signs are there to ensure that this here is a positive, and therefore the negative is going to be absorbed, and we shall have delta b is equal to magnitude delta x sine x. So the next step is we are going to substitute what we have here in this to get the maximum possible error in z. So let us do that. Therefore, maximum in z, which z, it is a over b, but a is equal to sine x, b is equal to cos x, is now equal to magnitude. The error in a is here. We have magnitude delta x cos x divided by a, but a is sine x. From here, a is sine x, b is cos x. So we are going to substitute in for delta b and b itself. So plus delta b, which is here, so delta x magnitude sine x divided by b itself, which is cos x. Okay, so we are looking out for the error in sine x all over cos x. Common factor is magnitude. So the next thing is we are going to operate on this. This here is the same as magnitude delta x into cos x all over sine x. This is cot x plus sine x all over cos x. This here is tan x. So this is what gives us the maximum possible error in sine x all over cos x. So they also gave us that the error, which is delta x, in measuring the angle is 0.5 degrees, and the angle itself, which is x, is 30 degrees. 30 degrees is a big angle, and therefore our calculator is not going to be in radians like the way we saw when we are dealing with Newton-Raphson method and those other methods of finding the root. So here our calculator is going to remain in degrees. So if we are to convert this 0.5, our error, which is delta x absolute, is now going to be pi by 360. I was only converting 0.5 to be in terms of pi. So we substitute it here. I'm going to substitute it in this equation here to get the maximum possible error when we have the error in measuring the angle as 0.5 degrees and x, the angle itself, being 30 degrees. So we are going to substitute there. Maximum error is now going to be equal to, where there is this delta x, I'm going to put there pi by 360 into bracket cot x, but x is now 30 from the question here. X is 30 plus tan 30. Cot x, which is 30 plus tan 30. So this here is equal to pi all over 360 into bracket. What is cot? Cot is 1 all over tan. It's the inverse of tan. So this is tan 30 plus tan of 30. So with our calculator in degrees, we are going to compute this value here as the maximum error in sine x all over cos x. So when you press on the calculator, we are going to get 0.0202, and this here is 4 decimal places. So having gone through this example, we need to have one tryout question, and then we call it a video. Given that the area of a triangle whose adjacent sides are of side A and B, and the angle between the sides is theta. This here is the expression for the area. Given that A is equal to 2.5 centimeters, B is equal to 3.4 centimeters, and theta is equal to 30 degrees. Now they need us to write the possible error in each measurement. that the tolerance is equal to half times 10 power negative n number of dp's. Then error made in the area. A and B are not differentiable functions, but sin theta is a differentiable function. And take note that but C value within which the area is expected to lie. They need us to find the interval. So with this, try it out. And if you are new here at EduMath, consider subscribing and hitting the notification bell. Sharing and recommending this channel to your friend is a formidable combination of you and me. From us, EduMath, we wish you the best and God bless you.